Okay, hi guys. It's Chem21 online. Okay, with me, Sir Ardy. We're going to be taking up substitution reactions, elimination reactions, and the importance of alkyl halides or organohalides for those reactions. Okay, so alkyl halides, just a little side thing. Naming them is easy. I'll leave that up to you. Preparing them, you've seen them before. You've used alkenes and you've added HX or X2 to prepare those. So that's something you should already know. Now, you can actually prepare them from alcohols as well, and I'll show you that right now. If I have a tertiary alcohol, I could easily react that with HX, so HCl, HBr, or HI. And that tertiary alcohol will then turn into its alkyl halide form via a substitution reaction. In fact, it's an Sn1 reaction. Okay, and we'll learn more about that later. Now, if I don't have a tertiary alcohol, there are actually special chemical reagents that we can use. Okay, so if I want to turn, let's say, in benzoin, it has a secondary alcohol, and turn that into a chlorine, so I want to chlorinate it, substitute it for a chlorine, I will use thionyl chloride or SOCl2. What if I want a brominating agent? Okay, a brominating agent, a good example would be phosphorus tribromide or PBr3. So again, I have a secondary or tertiary alcohol in butan-2-ol. And with PBr3, that turns into a 2-bromobutane. So it turns into a bromine group. So easy, just memorize that. Okay. The reason why we want to turn alcohols into alkyl halides is, again, alkyl halides are reactive in the ways, or actually they turn into more reactive species because they tend to be very good leaving groups. So we'll learn more about that later. Okay. Now we're going to go into the bread and butter of our lesson, which are substitution and elimination reactions. You've encountered them before, as I've taught twice already. We've used acetylide, which is a negatively charged carbon that's triple bonded to another carbon. And we've used that to attack either a methyl halide or a primary halide. In this case, this is 1 bromo, 1, 2, 3, 4, so butane. Okay, and I said that this negatively charged carbon is attracted to this chemical, to 1 bromobutane. Why? Because it is a polar molecule. So this bromine is electronegative, pulling the electrons away towards itself and away from this carbon. So this carbon ends up being partially positive. And then again, we always draw our arrows from the electron source, from something negative to something positive. I cannot emphasize that enough. Okay? So negatively charged carbon attacks from behind this partial positive carbon here. Partial positive. Okay? But since this carbon cannot take 5 bonds, it will use this or break this bond and give those electrons to bromine. And if we follow those arrows, you end up with this. So now the acetylide with its 2 carbons or whatever went and bonded to this carbon here, which used to be this one, leaving us with a bromide that left. Okay, so now bromine has 4 lone pairs and is negatively charged. Okay, when I taught this reaction, I also gave you guys a couple of new terms. This negative acetylide was attracted to the positive carbon. So it's what we call a nucleophile. So Nu. This bromine group left after the nucleophile attacked it, so it was replaced, remember? So now, instead of a butane with a bromine, I now have a butane with an acetyl group, okay, an acetylene group. And of course, the naming is this entire thing, but yeah, you could look at it that way. So it was a substitution reaction. So for something to substitute something, something comes in this case, it's a nucleophile, and something has to leave. And that thing that leaves is what we call the leaving group, or the LG, okay, in shorthand. Nucleophile, leaving group. And this, my friends, is our electrophile. It was what was attracted to the something that was negative. Electrophile. Okay. There. The reaction of acetylide with a primary or a methylic halide is what we call an Sn2 reaction. Okay? So S stands for substitution, N stands for nucleophilic because it's a nucleophile that attacks, and 2 stands for bimolecular, which means that there are two molecules involved in the most important step. Okay? This important step is what we call the backside attack. So this nucleophile, again, attracted to this positive carbon, so it will attack this, forming or letting this X leave. And it will turn into that. Now, what's shown here is not an intermediate, it's a transition state. Okay? So this bond is half forming, this bond is half breaking. Okay? What do you notice between our nucleophile attacking from the backside and now our product? Okay? The direction of our tetrahedral used to be facing the right. Okay? Nucleophile attacks, it turns into the symmetrical thing, 5 pentavalent carbon. Okay? And now, what do you notice? Our substrate, or our molecule now, is a tetrahedral pointing the other way. Okay? With this as our leaving group. Okay? Leaving group, nucleophile. What do you notice? The direction of our tetrahedral started to face the other way. Okay, sorry. Wala pa pala. It's what we call an inversion. Okay. Going back to our mechanism, okay, we have our reactants. They react, they form a transition state, meaning the top of a hill. A transition state is not an intermediate, it's not a product, it's an in-between state. And then it went immediately to form our products. Tetrahedral facing one direction, tetrahedral now facing the other direction. Okay, so this is the reaction coordinate or reaction profile of the Sn2 reaction. It's just one big hump leading to the products. From a slightly high energy product to a slightly more stable product with just one transition state in between. Okay. Now the Sn2 reaction, okay, is a backside attack. So something like a methyl bromide or a methyl halide, because it only has hydrogens and that's parang blocking its backside, then the nucleophile can easily attack. And that's why methylic carbons or methylic substances only either undergo Sn2 reactions or no reactions at all. Now, I have a methylic, a primary, a secondary, a tertiary. What if now I have a tertiary bromide? Okay? If you look at the space filling model, there's almost no space for the nucleophile to enter into that backside of the carbon over there. It's already hidden amongst all these methyl groups. So you cannot access it anymore. Even secondary. So that's why usually for an Sn2 reaction, we prefer having a primary as methylic or a primary. Secondary would be forcing it, but sometimes it can happen. But tertiary, it won't happen at all. You cannot at all access this carbon here. It's hidden. Another thing is that vinylic, meaning a halogen attached to a double bond, is also unreactive because it can't attack the backside of a pi bond. Neither can arylic or aryl halides. Okay, so no reaction. Now, another important facet or characteristic of Sn2 reaction is that it exhibits what we call inversion. In fact, it exhibits 100% inversion. Why? Because when you do that backside attack, okay, the tetrahedral flips like an umbrella flipping in the wind, okay? So if your leaving group was, let's say, pointing towards you, the incoming group has to go from behind. And so it'll attach from behind. So if it was once wedge, when the leaving group leaves and the incoming group enters in, the incoming group, the nucleophile, will now be, once it's attached, at a dashed position. And this could oftentimes mean that you could have, let's say, an S molecule and 100% of your product will be an R molecule. But note, it's not always true that an R becomes an S or an S becomes an R. Okay? What's only true is that the orientation of your tetrahedral changes. Because again, R and S depends on the priority. So the Cahn-Ingold Prelog priority numbers. Diba? When we prioritize via weight. Or sorry, atomic mass. So that's something you have to check manually again. Okay? But it will always be true that if, let's say, my leaving group was once attached via the wedge position, then my incoming group can only attach from the dashed position. So this, my friends, will be 100% of our product. That same phenomena of having your tetrahedral flip is a lot more evident with cyclic systems. Let's say a cis-1 bromo a 3-methylcyclopentane, when it gets attacked by, let's say, our nucleophile, in this case a hydroxide, you end up with a trans product again because now your incoming group can only attack from the back side or from the opposite side of your leaving group. So transition state, not an intermediate, and then your final product. Okay. Just a little note on nucleophiles. Nucleophiles can sometimes be negative or just neutral. Okay, just remember that you have to conserve charge. So if I have negative plus neutral, then you should know that your product should also be just negative charged overall. So minus and 0 is minus, so 0 plus minus is still minus. Okay, what if my nucleophile was neutral and my substrate was also neutral? So neutral plus neutral is neutral, but my leaving group leaves as an anion, which means my final product is positively charged. So that positive plus minus is still neutral. Just have to be careful with that. Just double check all your formal charges always. Okay. Depending on your nucleophile, you can have all sorts of different functional groups that you can create. So you can introduce a nitrile functional group, a thiol functional group. If you add cyanide or hydrosulfide ion, you can have an iodide. You can add an ether functional group. If you add an alkoxide, or this is a methoxide, an OH minus can create an alcohol, etc., etc. But note, these are only for methane or methylic substances, okay? Some of these reagents, if I use them for other kinds of alkyl halides, will get a mixture of other products. So just wait for that. Okay. Another important thing is that nucleophilicity has a lot to do with our reaction. So, being nucleophilic means, again, you're attracted to something positive, which means you're negative. Now, the thing about being negative is that, yes, you're attracted to positive carbons, but if you're too negative, oftentimes you can end up becoming basic. So, again, what is being basic? Basic means you want to grab a proton, okay? So again, grabbing a proton or grabbing a hydrogen from something. Let's say I have a base, I have water, or let's say an alcohol group, okay? Instead of going for the positive carbon somewhere there, the base will simply use its lone pair and get a proton, right? And deprotonate something. So that's a base. A nucleophile is something attracted to positive carbons. Okay? Now, basicity and nucleophilicity is a little bit tricky. Okay? More often than not, they parallel each other. So the more negative something is, let's say, the more concentrated its negative charge is, the more basic it is, and the more nucleophilic it is. But that's not super true. Okay. When you have a spread out negative charge, okay, here's the trick. If you have a negative charge, then of course you're more basic than something neutral. But let's pretend you have negative charges for everything. When you have a negative charge and it's concentrated too much on a single small space, then you actually become a lot more basic. And if you have a negative charge that's sort of spread out over a larger atom or a larger volume, then you actually are more nucleophilic. Okay? So the HS ion or an SH ion, like, okay, the hydrogen sulfide ion, is actually more nucleophilic than the hydroxide ion. The hydroxide ion is a lot more basic than this because oxygen is smaller, so it has a more concentrated negative charge. Sulfur is bigger than oxygen, so it has a less concentrated charge. But because this has a very concentrated charge, this tends to be a lot more basic, so this will rather grab a proton. Okay, the hydrogen sulfide ion, however, because it has such a large electron cloud, it has a negative charge that is a lot more stable. And since it's stable, it's patient. It can actually wait and go attack a positive carbon rather than be very impatient and be very unstable and grab a proton. Okay? So the same kind of rules apply for the halides, okay? If you going down the table, so chlorine is smaller than bromine, which is smaller than iodine, or rather, iodine is the biggest one of this series, and chlorine is the smallest. So since they all have just the same negative one charge, the iodide ion has the most spread out negative charge, and so it's the most nucleophilic. And chlorine has the most concentrated charge, so it's the most basic. Okay, so the fluoride ion is very basic. It's not very nucleophilic. Okay, its negative charge is concentrated over a small volume, and we call that kind of electron shell a hard shell. It's not very flexible, it's not very fluffy. So little bonding. An iodide, however, is a very big ion, but it still also has a negative charge, so it's still attracted to a positive carbon. But because it's has its electrons very loosely held because it's such a big atom already, then those atoms can simply or more easily penetrate into that positive carbon to form your or to have your backside attack. So can the softer it is, the more easy it can penetrate. Okay? So loosely held negative charge, more spread over, more nucleophilic. Harder, okay, or rather, more concentrated negative charge, okay, would rather grab a proton rather than bond to a positive carbon. So it's less nucleophilic. Now, so again, nucleophiles, good nucleophiles, negatively charged, usually spread over a bigger volume. So they have your sulfides, your iodides. But how about for bases? Now, bases are, they're all bases in a way, but a good way of spotting a strong base, at least in chemistry, is that these are usually the deprotonated forms of our common molecules that are either neutral or we just know them as non-acidic. Okay? Take, for example, the hydroxide ion. The hydroxide ion is actually deprotonated water, H2O. Okay? So the hydroxide ion is a small negatively charged ion and it just wants its proton back so it can become stable water. That's why it's very basic. How about, let's say, sodium amide? Remember amide NH2 minus? That's what we use to deprotonate acetylene to form an acetylide. So the amide ion is actually just a deprotonated ammonia. Ammonia is actually a very basic molecule. So ammonia itself wants to get protons. And then you remove a proton from it even more. So it becomes even more deprived, which makes it even more basic. That's why the amide ion is such a strong base. Not really nucleophilic, very, very basic. Ammonia can be sort of nucleophilic, but the amide is just this very strong, nasty base. Or how about if you have an alcohol? Let's say ethanol. You deprotonate ethanol, you get ethoxide. So the ethoxide ion doesn't want to stay as an ethoxide, it wants to turn back into its alcohol form. So it's just like an hydroxide. That's why ethoxide is a very strong base. Okay. What about something acidic like acetic acid? If we deprotonate acetic acid, it forms into an acetate ion, and that negative charge is resonance stabilized. So the acetate ion itself, since its negative charge is very stable or spread over, it's actually more nucleophilic than it is basic. It still is basic, but not very. Okay? So sabi niya, I can handle my negative charge. I don't need a proton so much. Okay. So some nucleophiles are more basic and some nucleophiles are just really nucleophilic. So take this table and sort of know it by heart. It's arranged by level of nucleophilicity. At the same time, they're also given a color coding. So if they're more basic than they are nucleophilic, they're red. So deprotonated alcohol, like a methoxide that came from methanol, hydroxide, which is deprotonated water. Okay. In this case, ammonia is still a base. And then notice that amide's not even on the list because the NH2 minus is just really, really a strong base. So take note of this list. This is not a comprehensive list, not a complete list, but it's definitely worth something. Now, there are some molecules that are completely basic and not at all nucleophilic. Okay? Because again, what does it mean to be nucleophilic? It means that you're something negative and you can attack a positive carbon. Now, take for example tert butoxide. Tert butoxide is the deprotonated alcohol form of tert butanol. Okay? So again, I have an alcohol, I'd remove its proton, it becomes a strong base because again, it wants to go back to its happy neutral alcohol form. Now, the reason why tert butanol isn't at all nucleophilic, or the reason it's only a pure base, is that to be able to become a nucleophile, this negative oxygen has to be able to attack a positive carbon. Let me draw something here. Here, okay. Let me draw a positive carbon. So group, group, group. positive. Or what if it were, yan, a tetrahedral? This negative O should be able to attack this carbon. What if this were all, let's say, these were all methyl groups? Okay. See, I put a Br here. So it's not positive. It's only partially positive. Okay. This oxygen itself already comes with so many bulky methyl groups. It's third butoxin and a carbon right behind it, a quaternary carbon. It's so bulky, there's so much steric hindrance, so it can't fit. It can't. This cannot fit and bond with this carbon, and it would rather grab a nearby proton instead. So third pentoxide is what we call a bulky base. And the thing about bulky bases is that we know that they will really just grab protons and they really cannot or they are not attracted to positive carbons almost at all. Now, aside from the strength of your nucleophile or your nucleophile being basic or not, okay, because if it's basic, it turns into some other reaction. Another important factor for our substitution reaction is our leaving group. Now, if you have something attached that doesn't want to leave or cannot leave as a stable anion, then even if a nucleophile is there and attacks your carbon, your leaving group won't leave, so it won't get substituted. There won't be any reaction. Okay. Chemists, okay, have a list or know a lot of very good leaving groups, and some of the best leaving groups in chemistry are what we call sulfonate groups. So here, they have an O, and then single bond S, double bond O, and then some sort of R group. So a tosylate is this, a mesylate is this. The tosylate is amazing because when these electrons land on this oxygen, they can turn into a pi bond here, and this one can go up here, okay, blah blah blah, and so much resonance can actually stabilize that negative charge. Same thing here, so much resonance to stabilize the negative charge. So kayang-kaya. This thing can really take negativity. Okay, or let's say a double bond here can go here, and the negative charge can go around this ring. Oh my god, so much resonance. Okay, so tosylate or mesylates are very good leaving groups. Okay, ammonia, water, iodide, bromide, chloride, they're all very good leaving groups. So these can all easily get replaced by some other nucleophile. There are two things you have to look out for leaving groups. One is fluoride. So fluoride is a very bad leaving group. That's why fluorinated substances are very stable, like Teflon. Another very bad leaving group is the hydroxide leaving group. So the hydroxide leaving group comes from an alcohol. That's why, prior to this, I already showed you guys that alcohols should be reacted or could be reacted and turned into alkyl halides. So tertiary alcohols with HX, secondary alcohols with SOCl2 or PBr3 to turn it either to a chlorine or to a bromine. Now, let's go back to this list first. Notice there's water here. Where does water come from? How is water leaving group? Water also actually comes from alcohols. But there's a thing. For alcohols to be able to turn, let's say you have an ROH. For alcohols to be able to turn into a good leaving group, which is water, they need to be in an acidic environment. So if there's an H plus somewhere there, okay, this will act as a base to grab a proton, and this now becomes a protonated alcohol, RO, with two hydrogens and one lone pair. And we all know that an oxygen with one lone pair and three bonds is positively charged. So now this can easily leave, and once it leaves, let's say after it's in an Sn2 reaction, it leaves as water. So 2 lone pairs instead of 1 a while ago, and still it's 2 hydrogens. So that's how it becomes water. It's a very good leaving group. Okay. So the same thing happens here. Amide is a very bad leaving group, NH2 minus. It's very unstable. In fact, it's very basic. But if you protonate arnamine, you can make it leave as ammonia. Okay. Now, aside from having a good nucleophile that isn't basic, and aside from having a good leaving group which can easily leave on its own, or rather not on its own, but once it gets forced out by the nucleophile with a backside attack, it can survive on its own. Another important factor for an Sn2 reaction would be the solvent of your system. There are two major types of polar solvents that we have, okay? We have polar protic solvents and we have polar aprotic solvents. Okay, sorry, we have nonpolar or polar solvents. We also have protic solvents or aprotic solvents. What does it mean for something to be protic? Okay, for something to be protic, it simply means it has a hydrogen bonded to an oxygen or a nitrogen. So an example would be, let's say, water. Water has an OH bond, so water is a polar protic solvent, since water is also polar. Alcohols, let's say ROH, they have an H bonded to an oxygen, so alcohols are also protic solvents. So they can be polar or apolar, or not sorry, non-polar, but they can also be protic or aprotic. For an SN2 reaction, we actually cannot have polar protic solvents. Why? If I have a polar protic solvent, I have an exceptionally positive hydrogen, which can hydrogen bond with your anion or your nucleophile. Okay? Your solvent will have such a strong bond to your nucleophile and it will form a cage around your nucleophile. And when your nucleophile is caged, it will have a difficult time doing the entire backside thing. Because not only is your backside already, protected by hydrogens and methyl groups or whatever, but now even the nucleophile is blocked from attacking the backside. Okay? So that's why we do not want polar protic solvents. We want polar aprotic solvents. So what's an example of something polar but not protic? Let's say acetone. Acetone is polar. Okay? Electrons go towards oxygen, but all of its hydrogens are bonded to just carbons. Okay? Or let's say ethyl acetate. Okay? So it's an ester. Esters are polar somehow. And again, they only have hydrogens bonded to their carbons. So again, polar protic. Or how about an ether? Right? A dimethyl ether. None of the hydrogens are bonded, but they still have an oxygen to sort of make it polar. There you go. So in summary, we have for SN2 reactions, number one, that since they're backside attacks, they cannot be blocked. So they usually happen for either methylic substrates or primary substrates. Another thing is that the substrate should have a good leaving group, let's say like halides. That's why we're taking up halides along with this chapter. Because if the leaving group does not want to leave, then we cannot substitute it. So wala tayong substitution reaction. Another thing is that we have to have a good nucleophile that isn't basic. So again, remember that something to be nucleophilic means it has a negative charge or it is partially negative. And that negative charge is more or less loosely held or spread over. Because if something is concentrated negative charge, that tends to be basic and unstable. Okay? Another important factors are solvent. Again, the reaction has to be done in a polar protic solvent. Sorry, polar aprotic solvent, because if it is done in a polar protic solvent, then your nucleophile gets trapped inside a solvent cage. So So an example again of polar aprotic solvents we can use for Sn2 would be acetones or ethers or esters. And then last is that the stereochemistry of our product will always be an inverted version of our original substrate. So again, think of that umbrella flip and remember the backside attack mechanism of this reaction. So here's a summary video that I think you guys might appreciate.
Primary halogenoalkanes undergo Sn2 reactions, where the S denotes a substitution reaction. The N shows the reaction involves a nucleophile. 2 is the number of species involved in the slowest rate-determining step. A nucleophile is an electron pair donor. It is attracted towards species carrying a full or partial positive charge, with which it can form a dative covalent bond. Consider the reaction between a hydroxide ion in solution and bromoethane. Both reactants are involved in determining the rate of the reaction in a one-step process. The hydroxide ion attacks the carbon atom from the opposite side to the halogen atom. Because the bromine atom, A, is so large it impedes the approach of the smaller hydroxide ion, and B, it repels the negative charge nucleophile. The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable transition state complex. The complex behaves like an umbrella blowing inside out as the bonds rearrange into a tetrahedral structure. A bromide ion, called the leaving group, is released. The transition state complex. Sn2.
There we go. Okay, let's try this item here. So I want you guys to arrange the following set, so for A, B, and C, with respect to the reactivity for Sn2. Okay? So now's the time to pause the video and try to answer this item. Okay, let's look at the answers now. Let's look at A. A, has 3 different kinds of chloride atom, chloroalkanes, okay? So you have a tertiary chloride, a primary chloride, and a secondary chloride. So Sn2 is a backside attack. So something that's tertiary should be unreactive, and something that's primary should be more reactive. In fact, the methylic would be the best. So this would be the least reactive. So primary is the most reactive, and this is just the middle. Example, bromide, bromide, bromide. So all the leading groups are the same. This is a 1 carbon, 2 carbon. Secondary bromide. This is attached to a first position, so it's a primary bromide, and this is also attached to the primary position. But note, this primary position has an isopropyl group attached to it. This position where the bromide has some sort of a tert butyl attached to it. So primary, secondary. So these 2 primaries are the best, but this primary has a bulky group attached to it. This primary has a less bulky group attached to it. So this should be the most reactive, followed by this, followed by this. Now the last, okay? I have an ether, a tosylate, and a bromide. So this will leave as a methoxide. This will leave as a tosylate. This will leave as a bromide. Again, in chemistry, we love tosylates and sulfonates and mesylates because they're amazingly good leaving groups. So this should be, they're all the same primary position. So this would be the most reactive, Bromides are also very stable. Methoxides are very bad leaving groups. So yan. So best leaving group, least steric hindrance, or primary substrate as well. Okay. For the next lectures, what if, we can answer a few more questions. Like, what if instead of a nucleophile, you use a strong base? Or what if we use the opposite condition? So, like, okay, bawal ang tertiary, but what if we do use a tertiary alkyl halide? Or what if we use a polar protic solvent, etc.? So that will be the substance, or rather be the content of our next lectures. Hope you guys enjoyed.